Okay, Assalamualaikum warahmatullahi wabarakatuh and hello. We continue our session with power. Okay, so power in AC circuit. Okay, so this is part. Okay, so remember you learn about instantaneous power. Okay, we dominated as small capital T, P and T, or P, small capital P. And then you have average power or P, capital P, or sometimes we call it real power. So you already learned these two, okay? And there are a lot also another power here, apparent, or no, reactive power. And then you have apparent power. Okay, reactive power, we call it Q. Okay, for this one, we are unit. Okay, the unit is W or watt. This one also W. Reactive power, we use the unit VAR. Okay, and apparent power, we usually call it S, and the unit is VA. And then you have a complex power. Okay, so basically you have 1, 2, 3, 4, 5. 5 power. Complex power, we also use S, but usually we bold it. Okay, bold the S. Okay, the difference is this one is amplitude. Okay, P amplitude, Q amplitude, but S is a complex. Okay, this one is also amplitude but change with time. This is constant, Q, S constant. Apparent power is a complex number. So in week 2, in the next study, we learn about the complex power and apparent power, but for complex power. But for today's class, we learn about the Q and S, this one. Okay, so we continue. So if you remember that the average power or real power, P is equals to 1/2 Vm Im cos theta V. Make sure theta V first minus theta I. Okay, the unit is watt. Now we move on to the reactive power. Okay, so what is reactive power? A real power. Okay, in real power, the power is absorbed by the resistor. Okay, the resistor. But in reactive power, it is absorbed by the inductor and capacitor. Okay, so reactive power is basically caused by the L and C. Okay, so how to calculate the reactive power? Almost the same formula here, but the difference is Q equals to 1/2 Vm Im. Instead of using cos, you're using sine. Theta V minus theta I. Okay, and the unit is VAR. Okay, so that is the difference. If you have a circuit here, for example, let me move it. Okay, if you have a circuit plus minus, AC circuit, okay, you have a resistance, inductor, and a capacitor here. Okay, the L and C and R. So the power absorbed by the resistance is P. Okay, power absorbed by the resistance is P. Power absorbed by the inductor is Q. And for capacitor, it is different because power supply by C is Q. Okay, so basically inductor supply absorb Q. Okay, capacitor, okay, L absorb Q. Okay, so C supply Q. Okay, why? Remember, for theta V and theta I, okay, for inductor, I is lagging. Okay, lagging means that, okay, contoh you have example here we have theta V here, VL, and this is I L. So laggings mean that theta V and theta V is 0, theta I is negative 90, you get theta is 90 degree. So sine 90 degree is 1. So means that your Q is equals to positive 1/2 VMIM. Okay, but if the capacitor is connected, okay, if you check here, okay, so for capacitor, so remember I is leading by 90 degree, means that theta V minus theta I is equals to theta V is 0 degree minus 90 degree, you get negative 90. Sine 90 degree is negative 90. Okay, negative. Sine negative 90 is negative 1. So Q is basically negative 1/2 VMIM. Okay. So when it comes to negative power, means that it is supply. So be careful. So in the note here, this is the formula and the unit VAR. Okay. Okay, this is the F. Now this is the PQ, the relationship. So what is the relationship between P and Q? Okay. So remember, I said that there you have a P, real power, Q, apparent power. Okay, for example, here this is P, you have the Q. When you combine this, you have the apparent power S. So basically, apparent power consider both P and Q. Okay, so that is the meaning of this note. Okay. Another way to calculate this is this one. Okay. You remember that the instantaneous power, I think this one, sometimes you can use it. So when you already know what is P, what is Q, PT is basically P, okay, plus P cos 2WT minus Q sine 2WT. Okay, this is another formula, you can memorize it. So PT, this one is basically P plus 1/2 VM IM cos WT plus theta V plus theta I. This one is basically another equation that you can use to calculate the instantaneous power. Okay. So this one already mentioned, when it is purely resistive, the power is this one and Q is 0. Okay. But if you have pure inductive, okay, the power is 0, the Q is 1/2 V max I max. So basically the instantaneous power is this one based on this formula. Okay, because power is 0, you just get Q equals to sine 2WT. Okay, negative sine Q 2T. Okay. Okay, for the purely capacitive, also, of course, P, the real power is 0. Q, you get negative. Remember that I showed you before, Q is negative and the instantaneous power is negative Q sine to T. Okay, this is what I have explained before. Okay, so this is the conclusion what I have been shown. Okay, reactive or active power. Okay, active power or real power or average power is positive. Reactive power is 0 for resistant. For inductor, this is the figure of the inductor. You can see here. Okay. Yeah, inductor here. The real power or average power is 0. Reactive power is positive. But for the capacitor, this is the image of the capacitor. Active power is also 0, but reactive power is negative. So that is the relationship between average, reactive, instantaneous, and apparent power. So how to calculate? Of course, this one is example. You can try to do it. Okay, maybe I just show you. Okay, you have I, you have Z. Okay, so you find the average power and the impedance delivered to the impedance, the average power. Of course, you have to calculate, find the V. Okay, equals to Iz equals to, I think this one already shown. Okay, find also the reactive power. So for the reactive power, instead of for the real power, you have to find the V 1/2 V max. Okay, you can see here, right? Max. Okay, so max means that you use the maximum value I max. Okay, cos theta V minus theta I. Okay, and okay, maybe I just show you 10 multiplied by is 200. 30 minus 20 is 8, right? 8 degree. So P, just use the formula. I think I already showed you the example before. But for Q is same formula. V max, I max, sine. Instead, of course, you use sine theta V minus theta I. Okay, because the question asks you reactive power, you use this formula. So this is how you use you answer question number example 2. Okay, this one you can also test it. Okay, consider the circuit below V1. Where is V1? The V1 is here. Is 120 angle 0, frequency 50 hertz. Average power absorbed. Okay, average power absorbed by the load before switch is closed. Before. Okay, so means that C is not considered. You only show the inductor and capacitor, and you can see here. This is in the time domain. So L is equals to 160 millihenry. You have to change it in frequency domain, which is ZL is equal to J 2 pi F. Okay, remember it is shown as frequency. You have to use this formula 2 pi F and then L. So J 2 pi F is 50, and then L is 0.16. Okay, make sure you know how to convert milli to this value. Okay, you can calculate it. Okay, and you can convert it and then find the average power absorbed. Of course, you have to calculate the current that passing through the passing through here. Okay, let me move it. Okay, so the power absorbed here, you can see that Q. Okay, so I is equals to, this is I. Okay, the capacitor just ignore because the power before the switch, just C is just redundant. So V divided by Z total equals to V is 120 degree angle 0, just leave it. Okay, and divide by 60 plus ZL, okay, in series. Okay, so you calculate I and then you find the P is equal to V, okay, 1/2 V max I max cos theta V minus theta I. Theta V is of course 0. Theta I, you have to calculate this. Okay, and then find the Q. Okay, of course, Q, the formula is almost the same. R max, I max, but instead of cos, using sine. Sine theta V minus theta I. Okay, this is how you do it. And then the third question is, okay, you have to practice this. Find the reactive power supply by the capacitor when the capacitor is closed. So for this case, of course, you have to calculate the Z total. So how to calculate Z total? Of course, it is parallel. Okay, you can calculate the ZC first. ZC is equals to negative J divided by 2 pi FC equals to ohm. And then after you get ZC, you calculate ZT is equals to ZC parallel with, okay, R plus ZL. Okay, so ZC ZL divided by ZC ZL plus R divided by ZC plus ZL plus R. Okay, and then after you get the Z, okay, after you get the Z, you find I, the new I come out from the source. Okay, I is equals to V source, okay, divided by V1, okay, V1 divided by ZT, you get the answer. And of course, you use the formula Q because it asks you to find the reactive power by the capacitor after the switch is closed. Oh, for this case, okay, find the reactive power supplied by the capacitor after the switch is closed. For this case, you don't need to do this. Okay, actually, you don't need to do this. Okay, because capacitor is in series. So you have to find the I is equals to, okay, this one if you want to find the total reactive power supply by the power source. But if you the question asks you to find the power supply by the capacitor only, it is much more easy because it is in parallel. So you have to find the I is equals to, okay, V1 divided by ZC. You get the capacitor, okay, voltage, the capacitor current, IC, not I. So IC is, okay, and then you just use the formula Q is equals to 1/2 VI max, then IC max, okay, sine theta V max, okay, minus theta IC, okay. Okay, depending on the question, if they ask the capacitor, you have to make sure you find the voltage and current at the capacitor. If they ask for the power supply, okay, you have to calculate at the voltage source. If the voltage source means that you have to calculate the total impedance. But if they ask the capacitor only, okay, you don't need to calculate the total impedance. You just find the current that passing through the capacitor. Okay, make sure you understand the question. P and Q at the what point? Okay, only at the capacitor you have to calculate the voltage and current at the capacitor only. Okay, that is how you done the question. Okay. Okay, this one you already understand it. Okay, instantaneous power, average power, type of AC power, RLC. Okay, and the effect of C and the reactive power. Okay, this one. Okay, remember that I said, okay, let me move it back. Okay, maybe this one. Sorry, my PC is hang right now. Let me pause it first. Okay, so let me show you. Okay, so for the resistance, remember that you absorb, okay, absorb power, active or real power or average power. For inductor, it absorb reactive power instead of active, okay. But the capacitor is quite different because it is not a power supply, okay. It is not a power supply, but it can supply supply reactive power. So for example, if you have inductor, okay, if you have inductor inside your circuit, okay, if you have inductor, you have to supply a lot of reactive power. You have to supply Q into the circuit. But if you have capacitor, you put capacitor inside the circuit, the reactive power will gone, okay? Because capacitor will supply the reactive power. So basically, what it means that, okay, because this is important because you will use this in the power factor correction as well at your assignment. So basically, the uniqueness of the capacitor is that when you have, okay, for example, if you have something like this, okay, if you have inductor, okay, if you have inductor here, okay, this one, this Q, for example, 100 VAR. But then you add capacitor, okay, instead of the 100 VAR is supplied by power supply, you add capacitor here, okay. For example, capacitor here can supply QC around 90 VAR, for example. Basically, the power supply only needs to supply 10 VAR. Okay, so basically capacitor can reduce the Q. Okay, but be careful. If you put too much Q, this one will become too much. Okay, so the supply by Q is too high to the power supply. So that is the relationship in the, okay, sorry, my PC hang again. Okay, so that is mean by the summary, okay, the effect of C element to the reactive power of the AC system is basically reduce, okay, it supply the power, reactive power, okay, Q, okay, not P, the Q. Okay, so we complete this part. We will continue with the effective or RMS value.